Hello, I hope everyone is doing great. I'm one of you aiming to build quality content in statistics. I believe together we can help each other grow. Let's start with the question. Here we have been given that x1, x2, xn is a random sample of size n from normal mu, sigma square. Mu is known and we have an estimator t equals to 1 upon n summation I goes from 1 to n mod of xi minus mu. We have to check if t is unbiased estimate for theta or not, and if not, we have to find an unbiased estimator of theta. It's very simple. We already know that mean deviation about mean is equal to 4 by 5 sigma. So we can simply write expected value of 1 upon n summation I goes from 1 to n xi minus mu mod equals to 4 by 5 sigma. Hence, 5 by 4 into t is unbiased estimate of sigma. Now, we will start with question 17.9. We have been given a population theta plus 1 x to the power theta. X takes value from 0 to 1 and theta is greater than minus 1. We have to show that t equals to minus of n minus 1 upon summation of log xi minus 1 is unbiased estimator of theta. These questions come very frequently in examinations, especially for whenever we have to do any kind of conversion from exponential to gamma or uniform to exponential. These are very popular and favorite questions. Let's go to the solution part. Here, I will try to analyze what is the distribution for log xi. So, considering minus log xi equals to yi. So, xi equals to e to the power minus y, dx equals to e to the power minus y dy. Hence, fx dx equals to fy e to the power minus y dy. Hence, we get theta plus 1 into putting x equals to e to the power minus y we get theta plus 1 e to the power minus theta y equals to fy into e to the power minus y, which is equal to theta plus 1 into e to the power minus theta plus 1 into y equals to fy. Hence, minus of log xi belongs to exponential theta plus 1. If we take summation, minus summation log xi belongs to gamma n, theta plus 1. Hence, we find expected value of 1 upon y, where y equals to minus summation log xi. Hence, we get that expectation of 1 upon y equals to theta plus 1 upon n minus 1. Hence, n minus 1 upon y minus 1 is an unbiased estimator of theta, which implies minus n minus 1 upon summation log xi minus 1 is an unbiased estimator of theta. Moving on to the next question. We have a truncated Poisson distribution with the given PMF, and we have to show that Tx equals to 0 when x is odd and 2 when x is even. Let's move on to the solution. Let's write down the PMF first. Our objective is to find an unbiased estimator of 1 minus e to the power minus theta based on the statistic defined as tx equals to 0 and 2. So we will consider expected value of tx equals to 1 minus exp minus theta. Here I am simply multiplying tx with the probability. So upon simplification we get the following form. Please write it down yourself, you will understand it better. Once we are able to find RHS as 2 times theta squared upon 2 factorial plus theta to the power 4 upon 4 factorial and so on, we will look into the LHS. Now, LHS can be solved as summation of tx into theta to the power x upon x factorial, which is equal to t1 theta to the power 1 upon 1 factorial plus t2 theta square upon 2 factorial and so on. Now, when we compare the like powers on LHS and RHS, we will find that tx takes value 0 if x is odd and 2 if x is even, hence proof. This is an example of an absurd estimator. We have been given that x1, x2 and x3 belong to uniform 0, 1 distribution, and we have been given some order statistics. Here, the easy approach is to find the distribution of each of the order statistics and then find their expected value and equate it or simplify it such that they become an unbiased estimator of theta. Such kind of questions are not very common in competitive exams, so I'm gonna skip it right now. Another question we have is 17.12, which is a very interesting question. We have x belonging to binomial distribution with parameters n, theta, and we have to find the unbiased estimate of theta and theta squared. Considering the next question where x belongs to uniform distribution with range 0, theta and we have two estimators, 2 upon n summation of xi and n plus 1 times maximum of xi's upon n. We have to show that both of them are unbiased for theta and evaluate the relative efficiency. Finding whether they are unbiased estimators or not is very easy. So, we see that both of them are unbiased estimators of theta. Now, we have to check the relative efficiency. Variance of theta 1 comes out to be theta square upon 3n and variance of theta 2 comes out to be theta square upon n into n minus 2. Hence, efficiency of theta 1 with respect to theta 2 equals to 3 upon n minus 2, which is less than 1. Hence, we see that variance of theta 2 is less than variance of theta 1. Hence, theta 2 is the most efficient and unbiased estimator of theta. Now we will solve 17.14 question number B. We have been given a distribution which is theta into x to the power theta minus 1 and we have z equals to minus summation of I goes from 1 to n log xi. We have to show that n minus 1 upon z is unbiased estimator of theta. Now taking zi equals to minus log xi, we obtain dxi equals to minus e to the power minus zi. Hence, Jacobian of transformation is e to the power minus zi. Putting all of these values and obtaining the transform distribution, we get that zi equals to minus log xi belongs to exponential distribution with parameter theta. Hence, z equals to summation of zi belongs to gamma distribution with parameters n and theta. Finding expected value of 1 upon z. So, expected value of 1 upon z equals to theta upon n minus 1. Hence, n minus 1 upon z is an unbiased estimator of theta. Let's move on to 17.15, Part A. We have been given Yn and Zn as two estimators of theta. Now we have to check whether they are unbiased or not. We see that expected value of yn equals to mn upon n plus 1, which is certainly not an unbiased estimator of theta. Here theta equals to m, and expected value of zn is equal to m into n plus 1 upon 2n, which is certainly not equal to m. Hence, both of these estimators are biased estimators. Now, we are interested in finding whether they are consistent estimators or not. For consistent estimators, we shall use the sufficient definition of consistency, which says that expected value of Tn tends to gamma theta and variance of Tn tends to 0, then Tn is a consistent estimator for gamma theta. These situations and conditions are valid only when n tends to infinity. So we find that variance of yn equals to n upon n plus 1 sigma square and variance of zn equals to n plus 1 into 2n plus 1 upon 6n square. So we will check the consistency. Expected value of yn equals to mn upon n plus 1, which tends to m as n tends to infinity, expected value of Zn tends to m by 2 if n tends to infinity. So Zn is certainly not consistent, but Yn is consistent for m. Now we shall calculate the efficiency. We have been given variance of Yn and variance of Zn. For computing the efficiency of Yn over Zn, we shall calculate variance of Zn upon variance of Y1. Similarly, we shall proceed with the B part. That's it for the video guys. Thank you so much for watching. Stay tuned.